Welcome back. For 6 episodes, we've been building a tokenizer entirely from scratch, byte-level byte-pair encoding, special tokens, the whole vocabulary. Today we finally hold it up against the production tokenizers that ship inside BPE and BPE. We'll load them with real libraries, tokenize the exact same paragraph, and compare token counts. You'll see that what you built is the same machine the big models use. Last episode we connected tokens to the model itself. A token ID is just a row number into the embedding table, and that's exactly why the strawberry trick fails. By the time the model reads the word, the individual letters are already gone. We also measured how the same sentence costs more tokens in some languages than others. Today we run those very same experiments, but on the tokenizers OpenAI and Google actually ship. There are 3 names worth knowing. TikToke is OpenAI's fast library for their GPT tokenizers. Hugging Face lets you load almost any open model's tokenizer in a single line. And SentencePiece is Google's trainer behind Llama, T5 and Gemma. Underneath them sit just 3 algorithms, BPE, WordPiece, and Unigram, and all of them are subword tokenizers, close cousins of the one you wrote yourself. Let's start with TikToke. After a pip install, loading a tokenizer is one call to get encoding. We fix one paragraph, a mix of prose, numbers, and a line of code and run it through 3 generations, GPT-2, CL100K from GPT 3.5 and 4, and O200K from GPT-4o. Each encode returns a plain list of integers, exactly like the encode you wrote. We just print the vocabulary size and how many tokens the paragraph became. Here's the real output. The paragraph is 249 characters. GPT-2's 50,000 token vocabulary needs 76 tokens. Double the vocabulary to CL100K and it drops to 69. Double again to O200K and it's 68. The trend is the lesson: a bigger vocabulary learns longer merges, so it packs more text into each token. Fewer tokens means cheaper API calls and longer effective context for the very same text. Picture it as a fan-out. One paragraph goes in at the top, and 4 different tokenizers each chop it their own way, producing 4 different counts. This is why token counts are never absolute, they are always relative to a specific tokenizer. When someone quotes a price per token or a context window in tokens, it only means something once you know which tokenizer drew the lines. Hugging Face generalizes this to almost any open model. AutoTokenizer from pretrained takes a model name, downloads the exact tokenizer that model shipped with its vocabulary, its merges, its config, and hands you an object with the same encode method. Here we load GPT-2's tokenizer and run our paragraph through it, then peek at how it splits the word strawberry. And look, Hugging Face GPT to tokenizer reports the same vocabulary size and the exact same 76 tokens that TikToke gave us. That's not a coincidence. 2 different libraries, written by 2 different teams, produce identical output because they implement the same BPE merges on the same vocabulary. The library is just packaging, the algorithm is the one you already built. And there's strawberry, split into ST, RAW, berry, the letters dissolved, just as episode 6 warned. Now let's load something that uses a genuinely different algorithm. But tokenizes with WordPiece, not BPE. The interface is identical, same from pretrained, same encode, but the merge rule underneath is different. WordPiece picks merges that most increase the likelihood of the training corpus, rather than just the most frequent pair. Watch how it marks continuation pieces. Same paragraph, 84 tokens, more than the GPT tokenizers, because BERT's vocabulary is smaller, only 30,000. Notice the double hash-onization. WordPiece flags pieces that continue a word, so the model can tell a word start from a mid-word fragment. And strawberry stays whole here because it happened to earn its own entry in BERT's vocabulary. Different algorithm, different vocabulary, different cuts for exactly the same text. Step back and the whole field fits on one slide. BPE merges the most frequent pair, that's GPT, Llama, and your tokenizer. WordPiece merges by likelihood gain, that's BERT, with its double hash pieces. Unigram starts with a huge candidate set and prunes the least useful pieces, that's T5 and Gemma. SentencePiece is the trainer and runtime that can run BPE or Unigram directly on raw text, which is why it handles languages without spaces so gracefully. So where does your tokenizer stand? Squarely in the family. Your from-scratch BPE is the same algorithm running inside GPT-2, CL100K, and O200K. The only differences are scale, how big the vocabulary, how much training text, and the regex pre-split. The production libraries are written in C and Rust, so they're dramatically faster, but the idea is identical. Even WordPiece and Unigram only swap the rule for choosing merges. The encode and decode contract you built is exactly the same. A few practical takeaways. If you care about cost or context, count tokens with the same tokenizer your model uses. TikTok for OpenAI, the model's own auto-tokenizer for open models. Context limits are token limits, so a more efficient tokenizer literally buys you more room. Switching models can shift your token count by 10 or 20% on identical text. And the biggest gaps show up in code, non-English languages, and rare words, exactly the places where the merges differ most. Let's recap. TikTok loads OpenAI's tokenizers, Hugging Face loads almost any open models, SentencePiece trains Llama-style ones. A bigger vocabulary packs more text per token. We watched the same paragraph drop from 76 to 68. And the three algorithm families all share the subword idea you've been building. Which means you are ready for the final. Next episode is the capstone. We package everything into a clean, installable tokenizer library, train it on a real text file, and stream encode a whole dataset to disk, the exact input the next course will feed to a GPT. See you there.